Hello, my name is Jouni Okela and I'm going to present the new type of drop structure. This is the same presentation I will be keeping in Hidroenergia 2014 in Istanbul. So this is the one made for YouTube. MEL-drop structure. The patent number is shown and this is the agenda shortly. First I'm going to explain the problems with low head dams, then the solution, the physical principle of it, about the energy control. There is the M square EL, which means minimum maximum energy loss. Then the benefits of this total energy control in energy production, and something about other aspects like river as reservoir, fish migration, sediment transportation and erosion. And finally a short summary. Problems with low head dams, and I mean the dams less than 3 meters or this level. So the most typical is the vertical hard basin. It's a dangerous drowning machine, so-called killer dam. It prevents fish migration or doesn't function in high flows. For example, with 1.8 meter head, that is a common limit for when the fish migration is normally kept as totally prevented. The maximum flow per linear meter is 6.4 cubic meters per second. It suffers from downstream erosion, but also sedimentation and debris deposition. So it has a quite high maintenance needs. This is still the same. One typical case, it is Ängsligen. There is a measurement station and a drop structure right beside. So here is a quarter of a cubic per second flow, 1.6 cubic, and it has a head of 0.7 meters, which outcomes 5.2 as a maximum, and here we have a situation with 7 cubics per linear meter. Here is the measurement data from the same time. So as you see, it doesn't work. Then there is a so-called sloping boulder ramp. It must be grouted, otherwise it has a miserable lifetime. It also suffers downstream erosion and has a limited capacity for energy dissipation. This particular slope were built in year 2000 in 1.1 million Swiss franc project FIMCA. It was updated 2006 with a 2.1 million project, and this photo is taken 2 years ago. The red is my bike, the head is 1.5 meter, so fish migration doesn't work. Then there is a so-called baffled chute, and which provides limited structural and aesthetic flexibility. It's expensive and therefore undesirable in most settings, despite it works. About the solution. So MEL structures is originally invented by Gordon McKay in Australia. Its US patent was given 1971. The further development patent is available, and it provides optimal water level heights through critical flow conditions throughout the whole structure. Yes, it's possible. For example, the critical velocity, also the velocity head, when we shall look from energy line, this is in measures. In the upstream side we have this height of velocity head, 1/3, and 2/3 is the critical depth. And when we go to the downstream, we can increase the velocity head as shown, and also the critical depth as shown, but as we have the same flow, we must make it narrower to keep up the continuity, and this is the way to go. So why critical flow is good? There will be no hydraulic jump, it will have no erosion and no sediment deposition, so it's in balance. Also the energy losses are at minimum, so it's practically the selection of the nature. Here's an aerial view of an MEL-culvert going beneath the Freeway. It's Brisbane, Australia, built in 1970s. The flow direction is shown, and here is an isometric projection of a dry MEL-drop structure with two turbines, the yellow ones, and the flow direction is also here shown. And as you see how it comes narrower and deeper, and to maintain the critical flow conditions. So about the energy control, minimum energy losses sounds weird, because the meaning of drop structure is to dissipate energy, but no, actually the meaning of drop structure is to control the energy line, and this means that if its dissipation ability should be small in low flows and high in high flows, following the needs of the rising flow velocity. And this is where all the existing drop structures fail. They tend to dissipate too much energy in low flows and too little, if any, in high flows, and the sedimentation and erosion follows accordingly. So about the energy control. So the blue lines show the minimum energy loss area, so where the flow direction is this. So first we have the full width, then we make it narrower and deeper. The water level is taken down without energy losses, and then the critical flow area widens back to full width, and there will be a vertical vortices and counter currents in this area after this nozzle, and in this area the energy line is taken down. And as the energy dissipation is based on vertical vortices instead of hydraulic jump, the drop structure can fully control both the upstream and the downstream flow. Videos from model tests are available on YouTube, so you can find it from through this link. So benefits of MEL structure in energy production. So here is a typical river flow and head duration diagram. This is R2 year 2011 data. The green line is the flow, and the red line here is the measured head, and the other red line is the calculated energy potential from these two values. And the yellow line is the potential head plus kinetic head, and the blue line is the MEL head. So actually it's a constant head, and the other blues and yellows are the energy lines accordingly. So when we go from downstream subcritical to critical, we can win this head, and we can win this much more energy. And when we go upstream and downstream, when we make the upstream and downstream variations parallel, we win a constant head, and which further means this much more energy potential. And with this structure it's even possible to have upstream flow critical and downstream subcritical, and this overflow makes the bump in available head. And this all finally sums up to 38.2% more energy production with a low head hydropower. Here is the same energy potential shown, the blue, yellow and red, and then there is turbines, 3 types of turbines, with and without a MEL structure. The orange ones are a Kaplan turbine without MEL and with MEL. Then there is a so-called Hidromatrix, so it's a propeller turbine and not regulated propeller turbine, and here is 3 turbines each. So there is the first step, second step and the third step, and here you can see the benefit from the MEL structure as we can maintain the constant head. Then there is the Jokela turbine, my own development, and the lower line is without MEL and the upper line is with MEL structure. So in figures that goes like this. When we compare a Kaplan turbine, 3 turbines, nominal flow, these turbines are same sized, we can have a 31% benefit with MEL structure. Yet the Kaplan turbine is difficult to place there because of the maintenance needs of the wicket gates and stuff. Okay, so with Hidromatrix we can have also approximately a 31% gain with energy production, comparing to Hidromatrix with or without MEL. And when we compare to Kaplan turbine we can have a 36% gain. And with Jokela turbine we can use the highest flow amount. So when we compare it to the Kaplan turbine we can have a 54% gain in energy production, this figure and this figure. And when we have a when we compare it with and without MEL we can have a 36% more energy production. And this example was calculated with the same river Are, Thun, with 2011 data and with nominal head of 2.4 meters. So other aspects, we could use the river as a reservoir, and with the same river the difference between actual yearly high flow water depth and critical water depth is 1.1 meter. So with MEL this difference could be used as an active water storage without losing the flooding capacity of the river. So if the river would be completely built between Thun and Bern, there will be a height for 46 meters available, the length of the river is 30 kilometers, the width 30 meters. It would be possible to store there 1 million cubic meters of water in the existing river. This would be enough to catch single heavy rainfall peaks to be later turbined or more interestingly used to store the night flow to cover the daytime needs. The primary benefits of these 19 pieces of 2.4 meter hydropower sets as shown above would of course be the production 240 gigawatt hours per year. Then about fish migration, the MEL structure is suitable only for low heads, and with certain assumptions we can build up following relations between the width of the river, the height of the drop and the flow as shown. And when we take the structure length similar as the width, which is quite nice, this would lead up to a slope of approximately 8%, and which means that the fish pass could be very easily integrated in the slope, and the fishes can thus find the pass very easily as it's middle of the main stream. About sediment transportation, in the blue area the flow is critical, in the absolutely critical in the nominal flow value, and due to the nature of structure the flow is near critical throughout the whole flow range. If sediment is deposited, it will happen here. The flow will vary to supercritical, and if it's eroded, the flow will vary to subcritical, and this should automatically pump the sediment downstream in the balanced matter. It should be also noted that the flow velocities are always average velocities, and the erosion depends actually from the actual velocity near the perimeter, which is shown here, so just to be noted. Summary. The MEL-drop structure can dissipate the energy throughout the flow range. It can control also the downstream side of flow, so no head loss on high flows will happen. And as no head loss, it means that up to 40% more energy potential with ultra low head hydropower would be available. Head loss, so during heavy rains the low head hydro loses head, okay, and so does also the mountains, as you can't see the peaks anymore, okay. But you know what? I'm convinced that the mountains doesn't lose their head either. They are just up in the clouds time to time. Thank you for your interest to my every word.